On to our next conserved quantity, and that's momentum. To change an object's momentum, mass times velocity, a force must be exerted for some amount of time. We call that impulse. Our impulse momentum theorem is J equals delta P equals F delta T, which tells us the area under the curve for a F times delta T graph is going to be our change in momentum. Or if we need instantaneous momentum, we can do F equals dp dt. Or if there's a varying force, our impulse is going to be the integral of F dt, which is also our change in momentum. Impulse, or change in momentum, is the area between the x-axis and the curve for a force versus time graph. Momentum is a vector, so direction matters. Momentum is not conserved when an external force is acting on an object or system. Energy is not conserved necessarily in the collisions. Usually we have to figure out the type of collision based on whether kinetic energy was conserved or not. Kinetic energy can be dissipated in any inelastic collision. Now for the types of collisions, remember that collisions are interactions between two or more objects or systems. They're not always car crashes. So you might have something hidden, a hidden interaction that maybe you don't see it as a collision, but is in fact a collision. Watch out for those. Momentum is always conserved in all collisions. This is for a very brief time, just before the collision happens and just after the collision happens. Elastic collisions have the same kinetic energy in the system before and after the collision. So if kinetic energy is conserved, it's an elastic collision. Perfectly or totally inelastic collisions means the objects stick together, so the initial momentum of 1 plus the initial momentum of 2 gives us one final momentum where we have combined masses. Explosions are the same thing but in reverse. We start with a combined momentum and then it splits off into 1, 2, or 100 different pieces.